All right, 4025 MEA mechanics, tutorial number 5. We are going to study the internal loads in this beam. So we have a beam here, which is constrained in A and B. We have a concentrated force of 9 kilonewton. We want to see what happens inside every point of this beam, because we want to draw the shear and moment diagrams for this simply supported beam. So how do we do that? Remember, first thing is always find the external forces. So step one, is always find all external forces. So in this case, reactions. How do you find the reaction? How many reaction forces we have for point A? So point A, what is it? Is it a pin joint or a roller or a fixed support? What kind of things it is? Go on. Anyone? What's the kind of constraint we have in A? I believe in A we have a pin joint. Yes, correct. So pin joint, that means we have two reaction forces that I will call AY and AX. And here we have a roller. It's very easy to see. And we'll call this BY. So if we write down the equilibrium equations, we have that for the X direction, Y direction, and around Z. Around Z, let's choose point A because it's easier. So in the X direction, we get that AX, of course, there is no action, so there is no reaction. We also know that AY minus 9 plus BY equals 0, doing this. So AY positive minus 9 plus BY equals 0. And for the moments, we have that this one is rotating clockwise and this is rotating counterclockwise. Oops, this is rotating counterclockwise. So what we have is that it's negative, it's positive BY times 6. So we have 6 BY minus 9 times 4 equal to 0. So that means that from this equation here, I get that BY equals 9 times 4 divided by 6, which is 9 times 4 divided by 6 kilonewtons. And from this equation, I get that, of course, AY must be 3 kilonewtons because the sum of AY and BY must balance the 9 kilonewtons level. So these are the external reactions, very important. And now that we know this, we have to find, so step two, identify how many segments are required and cut. So how many segments do we need to study this beam into? So since we have, remember the idea is that you can go from here to here and nothing happens. So you must stop in this region. This is segment 1. And that means that we have segment 2 here. Segment 1 goes from 0 to 4 meters, and segment 2 goes from 4 to 6 meters. So let me draw here a straight line. And we have segment 1. X goes from 0 to 4 meters. And segment 2, X goes from 4 meters to 6 meters. There you go. That's how it looks like. And so if I want to cut in segment 1 between 0 and 4, let's say I cut here. If I cut here, I can look left or I can look right. So where do you think I would look? What's easier? In this case, I think, since on the left we only have one force, AX is 0, AY is 3. So I'd say I'll look left. So looking left. And so if I look left, I have to draw everything that is on the left of this cut. So that means this, basically. The cut. This is point A, which, remember, has got a 3 kilonewton force. Here. And remember, we also have the, let me put here the convention. The convention is always this one. Where you have normal force. Shear forces. Then you have bending moments. B. So that means, since I'm using this convention, here. Since I'm looking left, I need to expose forces on the right. So since I only want what's happening in shear and bending, I will just expose these two. Also because I don't have any normal force, because there are no horizontal actions. So I cut here at a distance that is X meters away. Remember, this is X. X meters away. It says X is between 0 and 4. So that means that this distance here is exactly X. And so if I do the equilibrium equations now, I only need 2 equilibrium equations because I'm saying that the force is 0. Sorry, the normal force is 0, so I don't need the horizontal ones. So I get here that 3 minus V of X is 0, and I get that M of X minus 3X equals 0. Agreed? Looks to me that this moment is negative, and it's 3 times X. So that also means that I can rewrite this as V of X is minus 3, sorry, it's positive 3 kilonewtons, constant. And M of X is 3X, linear. Linear means equation of a straight line. Okay, so let's draw this later on, but let's start drawing this. This and this. This is the 4 meters. This is 4 meters. This is 0, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. This one is 6 meters. And this I will give m of x in kilonewton meters. And I will draw v of x in kilonewtons. Okay, so before we draw it, let's do the other side as well. So we've just done the first one. So let's draw the other one. The other one, will I be looking left or right? Now, if I cut here, which is in between 4 and 6, will I look left or will I look right? I think I'll look right because it's easier. So looking right. So let me draw the same thing, but now a small chunk on the right only. Remember, on the right, I have By, which was 6 kilonewtons. And then I have the left-hand side of the convention, which is m of x like this, and v of x upward like this. And now the question, how much is this distance? How much is this? Let's have a look. This is x. Remember, x is in between, this is x. So how much is this? What's this distance here? It's whatever is left. So it's 6 meters minus x. So it's this, the entire thing minus x, right? So this distance here is 6 minus x. Okay, now that we have everything, again, equilibrium equations, let's solve equilibrium. We have that v of x plus 6 equals 0. And then we have that m of x, so minus m of x, sorry, because this is negative, minus m of x clockwise, plus 6 times 6 minus x equals 0. If I rearrange this one, I get v of x is minus 6 kilonewtons, constant. And if I rearrange this one, I get that m of x is, if I arrange this one, m of x is minus 6x plus 36. And this is also linear. So it's the equation of a straight line. Okay. Now that we have found these ones, we can draw them. We can draw them very easily because what do you need? What do you need to draw a line? So how many points you need to draw a line? I think we only need 2 points. So that's what Euclid said. For every 2 points, there's only a straight line. So let's start with the shear. We have 3. Let's say this one is 3. This is 3 kilonewtons constantly between 0 and 4. But here, between 4 and 6, it's minus 6. So I'll go here, which is twice as much. This is minus 6. That's done for the shear force. For the bending moment, I need 2 points. So I'm going to use the moment at 0 and the moment at 4. So the moment at 0 is 0, because 3 times 0 is 0. The moment at 4 is 3 times 4, so that's 12. Let's say here, 12 kilonewton meters. And so I just draw a straight line between 0 and 4. And for this line, it's the same thing. I do m of 4, which is minus 24 plus 36 is still 12 kilonewton meters. And m of 6 is minus 36 plus 36, 0. So I start here again, and I end up here. This is the equation. This is the bending moment plot. And this is the shear force plot. Positive, negative, positive, positive. Okay, that's it. See how easy is this? Not very complicated. We just have to practice a little bit. Now let's do this one. This one is a beam, still a simply supported beam. See, this is exactly the same pin on the left, roller on the right. So it's exactly the same reaction forces. Call this AY and BY. I'm not going to use AX because see there are no horizontal reaction. There are no horizontal actions. So of course there will be AX is 0. So I will not even draw it. And now let's use the equilibrium equations to find reactions. So find reactions first. So how do we find the reaction forces here for this beam? So we only need 2 reactions, AY and BY, so only the Y and Z. Z, let's do it around A. So we have, first of all, we have a distributed load here. So how do we treat a distributed load? Distributed load is an equivalent force applied in the middle. In the middle means here. It must pass to the middle of this rectangle. So how much is this equivalent force? Remember, it's 300 newtons per meter times 4 meters. And this gives 1200 newtons. Agreed? That's what it is. So if I do my vertical equilibrium, I get that AY minus 1200 newtons plus BY equals 0. And if I do the moment equation, this moment is negative, this moment is positive. So I get 4 BY minus 1200 times, of course, this is 2 meters now, this is 2 meters. 1200 times 2 equals 0. So this means that from this equation, I get that BY is 600 newtons. Oh, no, I'm missing one thing. I'm missing this. There is a 300 Newton meter moment. So let me do the equation. This is a negative moment because it's clockwise. So again, minus 300 Newton meters equals 0. So I gather that from this, I get that BY equals 2400 minus 300 divided by 4. So 2400 minus 300 divided by 4, 525 newtons. Remember, newtons, we are looking at newtons here. And so that means that AY is 1200 minus 525, 675. So that means AY 675. These are the reaction forces. Okay, good. Now, how many segments do we need here? Remember, how many segments we need to study this beam to find the shear and moment diagrams? Apparently, we don't have any concentrated load. Remember, this equivalent load is not there, does not exist. It only exists when we do equilibrium. But what is there is a distributed load. So we don't need more than one segment. We can study this, we can study this beam using a single segment, S1. So let's say S1, X goes from 0 to 4 meters, because that's how long is the beam. So I can cut anywhere. Let's say I cut here, and I can look left or right. So let's look left. Again, it doesn't matter if you look left or right, but if I look left, I have to draw everything that is on the left. That is a 675 Newton force here, this here. And then I have to draw part of the distributed load. So it's not the entire distributed load, just the chunk that I'm cutting out, that I'm observing. And this one is 300 newtons per meter. All right. So what's, remember this is always with you, very important. So let's duplicate this so we know what we're doing. Let's put it here. So since I am exposing forces on the right, I'm using this convention here. This is V of X, and this is M of X. And how long is this part of the beam? Of course, this chunk that I cut out is just X meters long. And X goes from 0 to 4. Okay, so let's do equilibrium equations. Let me put this here so I can put the equilibrium equations over here. I get that V of X, sorry. I also have here, of course, an equivalent force. Put this down. A larger equivalent force. The equivalent force is in the middle of this. And how much is the equivalent force? It's 300 times X. Because it's spread over X meters. And so I have vertical equilibrium, it's 675 minus 300X minus V of X equals 0. And the moment equilibrium is 675 minus 675 times X plus 300X applied, of course, this distance is now X divided by 2 applied. So 300X of force, 300X of force times X divided by 2 of distance plus M of X equals 0. And so if I rearrange the first equation, I get, rearranging the first equation, I get that V of X is minus 300X plus 675, and this is linear. This is the equation of a straight line, remember? And this one is m of x equals minus 150x squared plus 675x. That's it. Yep. Equal nothing. So this is parabolic. So the parabola is ax squared plus bx plus c equals 0. Remember, this is the parabola. All right. Now that you have this parabolic description, we can also check, remember, one check that we can always do, check. Is the derivative of the moment in x is the shear force. So let's check. The derivative of this is minus 300x. The derivative of 675 is 675. So the derivative of 675x is 675. So this checks out. Okay. So we know that we are doing things correctly. Let me check these other ones that we found earlier. Derivative of minus 6x is minus 6. Derivative of 36 is 0. So this is also checks out. Derivative of 3x is 3. So this also checks out. Okay, so let me put this down. What we can do now is just draw. We draw everything. Let me draw this one and this one. We have to draw this between 0 and 4. Let's say this is 4. Okay. So let's say this is 1, this is 2, this is 3, this is 4. Okay, so let me remove this. Okay. So you tell me now, how many points do we need to draw the shear force? To draw the shear force V of x, which in this case is in newtons, and to draw the bending moment, in this case is in Newton meters. For the shear force, we need 2 points because it's a line, equation on a straight line. Nabu is asking, will we be given a graph page to draw, or will we just sketch in the exam? You can sketch it exactly as I'm doing it. I'm just sketching it, and that's completely fine. The only thing I want is you to write down all the interesting points. So at 0, it's 3. At 4, it's 12. At 6 is minus 6. And also, if this plot, as we're going to say now, this plot crosses 0, I also want you to find out where it does cross 0. Okay. Let me see how we can do this easy. So what I have here is that if this is 0, at 0, the shear force is 675. So let me say that this one here is 675 newtons. And when the shear force, when at 4 meters, the shear force is minus 1200 plus 675, which is, of course, is minus by. It's minus 525. If you don't trust me, you're welcome to find out for yourselves. Minus 525 newtons. So, of course, the straight line would be from here to here. Now, as you can see, this crosses 0 in a certain point. How much is this point? This is very interesting. This is an interesting thing that we want to find. So how do we find that? Well, you take this equation and you set it equal to 0. So you find that v of x equals 0. Let me put this here. Because here I say that v of x equals 0 means that minus 300x plus 675 equals 0. So that means that x equals 675 divided by 300, which is equal to 675 divided by 300, 2.25. And as you can see, it's exactly 2.25. So this is quite accurate, as you can see, because this point here is 2.25. That's what I want you to find. It's very important. So put 2.25 meters. Oh well. Okay, let's draw the moment. Now, the moment, we have a very interesting thing. We know that the derivative of the moment is v of x. So we know that the maximum of this parabola will always occur when this is 0. When the shear force is 0, you have the maximum. So we have 3 points now. We have the starting point, the ending point, and you also have the maximum point is here. So I will just find how much is m of 0. And m of 0 is, of course, 0. So I start from here. I find how much is m of 4, which is the ending point. So this is starting point. M of 4 is 150 times 16, 150 times 16, 2400 minus. Did I miss anything? I think I did. Oh, yes, guys, I'm missing something here. Remember, 300 Newton meters, it was here. So this is negative, so it must have been added here. So that means I must add 300 here. Okay, see, it's very easy to make mistakes, so make sure that you understand what's going on. So m of 0 is not 0, m of 0 is 300. And so that means I don't start from 0. I start from 300. And m of 4 is, I was saying, 675 times 4, which is, sorry, 675 times 4, 2700, plus 300 is 3000, minus 150 times 16, it's 600. So I end up at 600. Is it 4? Yes, 4. Do I end up at 600? Minus 150x squared. So 150 times 4 times 4. Okay, this is negative. Plus 675 times 4 plus 300. Is it possible? It should be minus 300. Oh, it's minus 300. Minus 300 here. So 300 minus 300 is 0. So I end up here. M of 4 is 0. This is the ending point. And so m of 2.5, because we know this is where it's maximum. So m of 2.5 is, let me check that, it's 2.5 squared, sorry, it's minus 150 squared. So minus 150 times 2.5 times 2.5 plus 675 times 2.5. And it's not 2.5, it's 2.25. 150 minus 150 times 2.25 squared plus 675 times 2.25 and minus 300. This gives 459.4. 459.4 Newton meters. 300 Newton meters. So we know this is very important. This is the largest maximum. So this is the maximum bending moment. It's, let's say here. Oh. Let's say here. This is 459.4. So my parabola looks like this. More or less. Okay. So this is completely positive, and the shear force is positive here and negative here. Any questions? To see what I'm doing here, it's very, very, very important that you know and you find all the interesting points for the entire diagrams. Okay, let's do the last one. Last one, a bit more complicated, but not too much. So let's go about it. So we also have here the same reactions, always the same reactions. It's pinned on this side, AY, and pinned on this side, CY. So reaction forces, find on this now, so I can say reactions first, reactions. For reactions, we have AY minus, remember, this is the equivalent load that is applied here in the middle. And this is 2 kilonewton meters times 5. This gives 10 kilonewtons. So minus 10 plus CY equals 0. And if I use Z around A, so this is the Y direction, if I use the Z around A, I get, this is negative. So CY, so it's 10 CY, because this is positive, times 10. 10 CY minus 10 times 2.5, this distance 2.5 meters. And again, this is also negative, minus 50. Everything is in kilonewton meters, yes, equals 0. So from this equation, I find CY, which is equal to 5 plus 2.5, should be 7.5 kilonewtons. Do you agree with me? 7.5 kilonewtons. I've done this by heart, but it should be correct. Yeah, it is correct. And that means that AY is the remaining 2.5. It must be. It must be, because both of them must sum up to 10 to compensate for distributed load. Okay, so how many segments do we need now? How many segments? We must study this beam in how many segments? Using 2 segments, S1, S2. So I'm going to divide this sheet in half. And I'm going to say that on the left, we have segment 1. Of course, segment 1 goes from 0 to 5 because something happens here. We have a concentrated moment. And we also have the end of the distributed load. They both happens all of a sudden. I'll say segment 1 and segment 2. Segment 1, x goes from 0 to 5 meters. Segment 2, x goes from 5 to 10 meters. So segment 1, I will likely look left, and segment 2, I'll look right. So looking left, and this is looking right. Let me copy the convention. Here. So I'm going to put this. Here. And so let's start. Let's give this a go. I'm just drawing what is on the left. What is on the left of this cut. And on the left of this cut, there is a chunk of distributed load and the 2.5 kilonewton force. This is 2.5. There's this side. And on top, we have the chunk of distributed load, which is also cut. This is 2 kilonewtons per meter. Of course, you have an equivalent force applied in the middle. This distance is x. And for the convention, we have this is m of x, and this is v of x. As it's always the same thing, it never changes. So we do equilibrium equations. For v of x, we have 2.5 minus the equivalent force is 2x. It's 2 times x. And minus v of x equals 0. And for the moment, we have minus 2.5x plus 2x plus 2x times x divided by 2. Remember, this distance is x divided by 2. And then plus m of x equals 0. Yeah, that's all we have. And so if I rearrange this equation, both of these equations, I get that v of x is minus 2x plus 2.5 linear, and m of x is minus x squared plus 2.5x. This is parabolic. As you can see, derivative of this is this, derivative of this is this. So this checks out. Let me write here, okay, because we checked it out. Let's do this other one. Again, I say I'm looking right, so I'm going to draw this side now. Shorter. Of course, if I cut here and look right, I have to draw everything that is on the right. So that means just the 7.5 kilonewton load. And of course, the correct convention, which is this one. What's this distance? Very important is how much is this? Have a look. This is always x always from the start of the beam to the cut. So this is 10 minus x. This distance here is 10 minus x. Okay, now that we have this, let's do the equilibrium equations. So we have v of x plus 7.5 equals 0. And for the moments, we have minus m of x plus 7.5 times 10 minus x equals 0. So let's rearrange this as well. Let's arrange this as well. Let me put this a bit up. If I rearrange these ones as well, I get v of x is minus 7.5 constant because it doesn't depend on x. Quite easy to see. And m of x is minus 7.5x plus 75. Yes. And this is linear. Okay, let me check the derivative. Derivative of this is this. Derivative of 75 is 0. Very good. This means also checks out. So now we can draw the result. So let's draw this. This is so let's see, minus 7.5 minus 2x plus 2.5. Yeah. This is 5. So the same distance because we have 5 and 5. So we have, this is 5, this is 10, this is m of x in kilonewton meters, and v of x is in kilonewtons. So we have linear here. So on the left-hand side, I have linear, and on the right-hand side, I have constant. Well, the constant one is easy, but let's start from the linear one. Linear one, I need v of 0. So this is 0. V of 0 is 2.5. This is 2.5. Say this is 2.5. No, let me drag this over here. I think I'm gonna need it. I'm gonna need more space on the bottom than at the top. Okay. And so I was saying this is 2.5. And then at 5, I got minus 10 plus 2.5. So I got minus 7.5. So 2.5, 7.5 is 3 times as much. 1, 2, 3. So it's about here. So this goes here. And finally, we have that from now on, this is always constant 7.5. So let me put this here so it's clear for everyone. This is still minus 7.5. See, minus 7.5. Now let's have a look at the moment. The moment I need 3 points. So let me find out what's this point first. What's this point? So I have to find where is this 0. And that is 0 at 2.5 divided by 2. So 2.5 divided by 2. This point is 1.25. This point is 1.25. So I can find now the moment at 0, 5, and 1.25. At 0, I have 0. Very easy. At 5, I have minus 25 plus this. So minus 25 plus 2.5 times 5. It's minus 12.5. So let's say here, minus 12.5. And the maximum point is at 1.25. So it's minus 1.25 squared plus 2.5 times 1.25. It's 1.56. 1.56. So let's say it's here. We put this down. Put this here. This is 1.26. So the parabola looks like this. Okay. And this one on this side, I do at 5 and 10. It's linear, so I only need 2 points. So at 5 is minus 7.5 times 5 plus 75. It's 37.5. So the moment here is 37.5. We have a large jump. Say here, 37.5. And at 10, well, at 10 is minus 75 plus 75. So it stops here. So this is quite more complicated. And you have here that the bending moment is positive here, negative here, and positive here. And the shear force is positive here, negative here, and negative here, negative everywhere. Okay, is there another interesting point? Yes, there is another interesting point. It's the last one. The interesting point is where the bending moment here is 0. So how much is this point? How do you find out? Well, you put this one equal to 0 and find out where it happens. So m of x equal to 0, that means that this is equal to 0. I can rewrite this as, agreed? This looks like, this one is like this. If I take x as a subject, so that means that this point here, this gives the first solution. So this is 0 when this is 0, when x is 0, of course, we found out. So this is the other solution. This is 0 when x is 2.5. So I know that this point here is 2.5. There you go. Okay. Any questions? Any questions, guys? No? As you can see, they are not complicated. You just have to do all the same things all over again. So the hardest, the most complicated part possibly is drawing these, but these are very easy if you have done a bit of algebra and calculus and understanding a bit of linear algebra and geometry, which you are doing right now in mathematics, I believe. Of course, I upload everything onto Aula. So as soon as I'm done with this, as soon as the recording is ready, I will put this under the tutorial section in week 5. That's what I always do. So if you look at all the previous weeks under the tutorial, there is this paper here, this one, and the recording of the video for every week. All right, guys, I told you I have to go away at 3. It's 1 minute to 3. So I think we've done this very, very, very perfect. And I'm going to stop recording right now.